Welcome to the Global Oceans 20 conference. We're excited that you decided to join our workshop, Collaboration for Marine Renewable Energy Environmental Monitoring Guidelines. I'm Alicia Emerson, the Program Manager for the Triton Initiative at the Pacific Northwest National Laboratory in Sequim, Washington. We are researching ways to reduce barriers associated to the implementation of marine renewable energy through environmental monitoring and technology development. With the help of our sponsors, the U.S. Department of Energy Water Powers Technologies Office. During this workshop, you will hear from various experts on our team. They're going to talk more about their research in environmental monitoring and specific stressors identified in the State of the Science report. Prior to starting at PNNL, I earned a master's in marine conservation and biodiversity at Scripps Institution of Oceanography. And while I was there, I researched whale watching sustainability and the use of guidelines for whale watching. This led me to create a working group also to look at ethical drone flights around wildlife. So between looking at sustainability in whale watching and drone sustainability, I'm now working in the future development of guidelines and recommendations for marine renewable energy installations. And for the duration of this workshop, I'll be moderating alongside my colleague, Kayleen Gunn.
Hi, I'm Kayleen Gunn. I'm an earth scientist with a background in ecological restoration and habitat monitoring of ecosystems along the entire terrestrial aquatic interface. But over the past several years at PNNL, I have worked on many aspects of the Triton initiative, including field research, communicating the science we do to diverse audiences, and all sorts of different projects. I now lead communications and outreach for Triton, and I look forward to hearing from you about Triton's work and how we can all work together to improve environmental monitoring practices and progress the marine renewable energy industry. And now I'd like to introduce you to the rest of our team. Take it away, Joe.
Hi, I'm Joe. I lead the underwater noise stressor. I'm the newest member of the team, joining PNNL 3 months ago, last June, and I am the new Triton PI. I have nearly 20 years of experience in ocean acoustics, working previously at NOAA's Pacific Marine Environmental Laboratories Acoustics Program at Oregon State University in Newport. And I lead the acoustic monitoring for the Wave Energy Device Testing Facility project known as PACWave off the Central Oregon coast. I'm also an avid surfer, and I enjoy any time I can get in the water.
Hi, my name's Molly. I lead the electromagnetic field stressor. I'm an ocean engineer and an aspiring marine biologist, and I'm also fascinated by the world of marine policy. Before joining PNNL earlier this year, I led the National Science Foundation's ocean policy portfolio. That job helped me understand the importance of policy, like the Triton Initiative's work to create guidelines. I completed a PhD at the University of Washington, focusing on the collision risk between tidal turbines and marine mammals. I particularly enjoy projects that combine my engineering expertise with better understanding the marine ecosystem, like understanding the environmental effects of electromagnetic fields.
Hello, it's great to be a part of this presentation. My name is Garrett Staines, and I'm a research scientist with a background in fish biology and behavior. I worked at the University of Maine School of Marine Sciences for 5 years. Most of my time was conducting research about fish behavior around tidal power turbines in the Bay of Fundy. I came to the lab in 2016 and have been working with the Triton team from the start, and it fills most of my time. I've filled several roles with Triton, and my main effort at present is researching interactions of marine animals with various current energy converters, like turbines. A main part of this work is determining the best sensors and methods to monitor these interactions, with collision risk being the biggest concern. I'm passionate about environmental monitoring and look forward to sharing with and learning from you.
I'm Linnaig MRE. I am the lead of the changes in habitat stressor. I'm a basic ecologist and marine energy specialist. I graduated from the National Museum of Natural History in Paris, France, with a PhD in ecology and evolution. And then I moved to the Oregon coast for a postdoctoral position at Hatfield Marine Science Center, focusing on the habitat characterization of various offshore energy sites along the West Coast, before joining PNNL a year and a half ago. And so like many marine ecologists, I have a multidisciplinary background that involves lots of field work from the intertidal to the deep seas in all sea states, but also lab work on plenty of office time.
The Triton initiative supports industry partners, innovates technology, and performs tests to explore the best methods in technology for environmental monitoring around marine renewable energy devices. As an extension of the programmatic work to bring forward environmental monitoring technology, the Triton initiative is moving into the next stage with the Triton field trials. And once we have the technology, we need to better understand the applications in the various marine, coastal, and pelagic conditions where marine renewable energy devices will be installed. And since 2019, the Triton team has identified 4 stressors that are linked to marine renewable energy: underwater noise, electromagnetic fields, collision risk, and benthic or pelagic changes in habitat. And these are the ones that we would focus on for our future research. Once we determined the stressor groups, we outlined field studies and literature reviews to better understand what technology, models, and monitoring programs existed. The final deliverable from this effort is a set of monitoring and technology recommendations based on scientific evidence. And we're asking for your participation in the creation of these recommendations so that our science is informed and supports those who will use it.
The Marine and Coastal Research Laboratory, or MACRL, is the U.S. Department of Energy's only marine facility. At MACRL, we conduct diverse research focusing on coastal resiliency, sustainable energy, and robust security of marine and coastal environments. We are located in Sequim, Washington, in the Pacific Northwest region of the United States, as you can see here on the map. Our laboratory is located at the entrance of Sequim Bay along a strong tidal channel. Sequim Bay is a relatively undisturbed embayment that leads to the Strait of Juan de Fuca, which connects to the Pacific Ocean. Our unique location, in combination with our suite of vessels, laboratories, facilities, and equipment, enables us to perform diverse research. As you can see in this figure on this slide, our small facility in Sequim supports a breadth of studies from field testing right in Sequim Bay to trace contaminants research in clean laboratory settings. The main areas of research at MACRL include algal biofuels research, wetlands ecology and biogeochemical cycling, ecological modeling, analytical chemistry, and of course, monitoring the environmental impacts of marine renewable energy.
Now it's time to hand over the microphone to our lead experts who are here to discuss the various stressors we'll focus on over the course of the next year. So let's get started.
All right, I will introduce Joe Haxel, who is the task lead for the underwater noise stressor. Go ahead, Joe.
Thanks, Kayleen. So many marine animals, including marine mammals, fish, and invertebrates are sensitive to acoustic conditions and use sound in the ocean for a variety of critical life functions, some of which include communication, foraging, navigation, and reproduction. The importance of the acoustic environment for many of these marine species is a key concern for maintaining healthy coastal ecosystems. The introduction of marine renewable energy projects into these areas has raised concerns related to the uncertainties that are surrounding MRE, radiated noise levels, the effective frequencies, and the duration or potential of exposure of elevated sound levels to these animals in these sensitive habitats. So as an example, underwater sounds recorded from a wave energy converter test site at the PacWave North testing facility off Newport, Oregon, shown here in the slide, show a frequency modulated tonal harmonic signal that oscillates with wave periods, and they're relatively similar in the frequency range and structure of some common humpback whale vocalizations. So this sound recording, as we'll play it for you, highlights the importance of measuring and characterizing the acoustic contributions of MRE-related underwater noise to ambient sound levels in these sensitive ecological areas. So some things we want to address are, what technologies and methods best measure and evaluate changes in acoustic conditions from MRE projects? We want technically rigorous and standardized methods to do this. We need them to be cost effective and also meet regulatory requirements. So here I'd like to stop and recognize the efforts of both the Ocean Energy Systems Environmental, or OES Environmental, and the Kearns and West Sandia Environmental Cost Compliance Assessment projects that have moved the needle significantly forward on this topic. So fortunately, some headway has already been made with regards to the technical approach for characterizing underwater noise with the 2019 release of an International Electrotechnical Commission, or IEC, technical specification for the acoustic characterization of marine energy converters. This document provides technical guidance for standardized acoustic measurements for MRE, but has not been fully put to practice in the US due to a lack of MRE installations. So through the Triton Field Trials, or TFIT campaign, PNNL is aiming to provide experience with the application of the IEC standards for measuring underwater noise at operational MRE project sites. So using commercial off-the-shelf drifting hydrophone technologies from Ocean Sonics, shown in the picture there, we plan to perform 2 field measurement efforts from active turbine installations. One at the University of New Hampshire Living Bridge, an experimental tidal energy platform at the Portsmouth Memorial Bridge, and a second at the Alaska Hydrokinetic Energy Research Center on the Tanana River Hydrokinetic Test Site, a high-energy riverine turbine testing site. During each of these field trials, we'll exercise the IEC technical specification guidance using commercial off-the-shelf technologies to provide characterization of the acoustic contributions of these turbines. From these field efforts, combined with input from developers, researchers, and regulators, we hope to develop practical guidelines that merge the IEC technical specifications with cost-efficient commercial off-the-shelf technology and methodology recommendations that also help to streamline permitting and environmental monitoring efforts. Thank you.
Thank you for sharing all of the information, Joe. Now I'd like to pass the microphone over to Molly Greer, who's going to talk about electromagnetic field stressor.
Thanks, Alicia. So electromagnetic fields, often referred to as EMF, exist throughout the world's oceans naturally, and many animals have evolved the abilities to sense these fluctuations and use these cues to find prey, to navigate, or migrate. As cables are installed throughout the world's oceans for electricity or telecommunications, these electrosensitive animals may be impacted by the disruption of natural electromagnetic fields with these man-made fields. Sharks, rays, and skates are known to be particularly sensitive to electromagnetic fields, as they are known to use them to sense prey and possibly use them for other activities. Other studies have shown that lobsters and crustaceans may also have behavioral responses to man-made electromagnetic fields. For marine renewable energy devices, there are EMFs generated by both the cable transmitting electricity back to shore, as well as the device itself. At present, the intensity and variability of the magnetic fields generated are still largely unknown. Further, we don't know if highly energetic sites where marine renewable energy devices would be installed are any different than a less energetic site. The electromagnetic fields generated from electricity transmission underwater are typically of a similar magnitude to the background magnetic field of the Earth, so it is challenging to accurately measure the fields and quantify the effects they're having on organisms. The Triton field trials for EMF is designed to determine which methods would best measure magnetic fields generated by a marine renewable energy device. In summer 2020, the Triton EMF team deployed a cable in Squim Bay to use to evaluate 2 different measurement devices. One, a C-SPY 2, which is purpose-built for measuring magnetic fields, and 2, a Yoast TSS MUSB, which has a magnetometer as part of its inertial measurement unit, which could potentially be used and is low cost, though is not primarily designed to detect magnetic anomalies. Both AC and DC currents were tested in 2 configurations in Squim Bay. A variety of tidal current rates were examined to understand the tide's impact on the strength and our ability to measure the magnetic field. Additionally, a point source generator was deployed to mimic the electromagnetic fields generated by a device, such as a tidal turbine. Initial analysis of the data shows that to reliably detect the cable, it is essential to have a background data set for the site or to know precisely where the cable is laid already. In 2021, additional field trials may be conducted in concert with the other stressor testing, such as at a wave energy site. Another possibility is measuring electromagnetic field strength and intensity of a different existing underwater cable, like those deployed for the Ocean Observatory's initiative in Washington State. These additional methods will ultimately allow the team to create reliable guidelines for measuring and assessing the impacts of electromagnetic fields at marine renewable energy sites.
Thank you so much, Molly. Up next, we have Garrett Staines discussing the collision risk stressor.
Thank you, Kayleen. Collision risk for animals and turbines. Typical turbine applications are in areas of fast tidal or river currents. In the US, there have been deployments in the East River in New York, Cobb's Cove in Maine, and the Kvichak River in Alaska. And there are several other deployments that have occurred in Europe. Risk concerns are usually with marine mammals, fish, and seabirds, especially diving birds. And several legal statutes protect these animals in numerous countries. Endangered or threatened species are obviously of high concern, as impacts to a single individual could have impacts on the population or ecologically significant unit. Research and device monitoring on this topic has been ongoing for over a decade, with no documented collision events. However, uncertainty for collision risk remains high due to the difficulty of effectively monitoring for collision events. In other words, the locations where monitoring must take place is inhospitable to usual applications of sensors. This has led to research on new technology and new applications of existing technology. With actual collision events being difficult to observe, as just described, encounter risk estimates using models have been informative to date. They help to show use of the area around a turbine and how likely an animal is to approach or get near a device. This is a good first estimate and may be enough to properly inform regulators depending on data needs. Furthermore, little is known about the consequences, injury or death, to an animal after a collision event. This could be no effect at all, it could be minor, scale loss or bruising, or the injury could lead to death. And there has been some research on this topic to date for marine mammals as well as for fish. The uncertainty related to collision risk often leads regulators, using the precautionary principle, to require collision monitoring during device operation. This provides empirical data for direct quantification of events and also to validate collision risk models if those are used as part of the monitoring. This monitoring requirement adds significant time and money to developer budgets and can be burdensome enough to prevent projects from device installation and testing. However, it is this required empirical data of animal behavior around turbines that is key to building a record for a knowledge base to reference as more turbine projects become operational. This requires quality data that regulators will have confidence in, and achieving this will depend on appropriate methods and sensors for monitoring data at project sites. The question is, how can we ensure this? To date, research has included modeling, telemetry for tracking individuals, passive acoustic vocalization detection for presence or absence, and even 3D localization, and flume studies with fish and small turbines in controlled lab settings. Sensors used to date include hydrophones, visual surveys, so just human observers, single beam fisheries echo sounders, multi-beam echo sounders, acoustic cameras, and video cameras. And a significant challenge is a large data set accumulations and difficult with analysis in a timely manner. As collision is likely a rare event, a means of analyzing all data, not subsampling, is important, but also challenging. How can we gather meaningful data with the most appropriate sensors? Triton Field Trials is answering these questions to provide the tools to achieve this. Triton Field Trials is currently tackling the challenge of observing and recording collision near-miss events and animal behavior with turbines. This requires sensors that provide high resolution at close range to a turbine. Video and acoustic cameras are ideal for this situation. Video cameras provide high quality resolution data if water clarity and light are sufficient, and if not, acoustic cameras or imaging sonars can fill in this gap. Furthermore, these data, in addition to providing informative empirical data to regulators, will also provide key inputs and models that are sensitive to animal behavior, such as avoidance and evasion near a turbine. Thanks.
Thank you, Garrett, for sharing the collision risk stressor. Now let's hand over the mic to Lynette Henry, where she will talk about changes in habitat stressor.
Thank you, Alicia. So changes in habitat is a broad stressor that includes all sorts of modifications to benthic and pelagic species communities. We are talking here about changes in species composition, abundance, and distribution within those communities. This stressor is also about the alteration of the physical habitat of the species, the sediments they live in that can become flushed away, the rocks they live on that can get crossed by cables, and the water column they swim in that can become occupied by devices and cables. Here we are interested in both the benthic organisms, those that live in and on the seafloor, and the pelagic organisms, those that live in the water column. And we are looking at both small and large spatiotemporal scales, since these effects could be expected right on a wave or tidal energy device itself, or several of hundreds of meters away, and right as devices are deployed, or several years into the operational phase. Changes in habitat can take the shape of many different effects, some more easily observable and measurable than others. The footprint and scour effects are observed right at the base of a device or mooring system, where the influence is the strongest. These effects are respectively the loss of habitat right where a device or associated equipment are installed, and the flushing of fine sediment like silt due to the increased turbulences around the base of a device. We can also expect changes in species composition within the sediment and on top as we get closer to a device or a cable. Over time, devices will get colonized by sessile and biofouling organisms, which will provide food and shelter to mobile animals, such as fish, leading to devices acting like artificial reef and fish aggregating devices. Over time, we can anticipate some areas with MRE devices to work like a marine reserve if fishing activities are excluded, with cascading effects up and down the entire food web. We can rely on many different methods and instruments to observe and measure changes in habitats around MRE installations. Several of these methods and instruments have been developed and employed for decades in other fields such as fisheries, marine ecology, or marine conservation. Depending on the targets and objectives, these tools can be sonars, cores, or grabs, trawls, video and photo imaging instruments, or other methods to collect data such as scrape samples on a scuba diver transect. The diversity of methods leads to a variety of metrics being collected and to difficulties in obtaining consistency among sites and projects for meaningful comparison and transfer of data and information. So our goal in TFIT with this stressor is to identify sampling methods that would bring the most consistent results for monitoring changes in the habitat at MRE sites. To reach this goal, we started by discussing with subject matter experts about the applicability of several methods. We are now in the process of conducting a thorough literature review of the methods used at MRE sites worldwide and in analogous industries such as offshore wind or oil and gas development. This literature review will allow us to highlight the pros and cons of each method and identify those better suited for the MRE context. We will then test at MRE sites a few methods that either need refinement or are new to the MRE context and promising. We hope to be able to eventually propose guidelines on best practices for assessing changes in habitats at MRE project sites.
Thank you, Leeds, for sharing all of that information about the 4 different stressors that we're working on in TFIT. And now we want to open up the floor. There's a couple questions Kayleen and I want to ask each one of you. And as we move through this next section, please Feel free, if we ask a question to somebody and you want to answer it too, bring your knowledge base. And so all questions are open for everybody. So the first question that we have is for you, Joe. What are the main sources of uncertainty in your work?
I would say the largest source of uncertainty right now for underwater noise is the actual devices themselves, source levels from the devices. Since we haven't had a lot of installations or projects in the water, we don't have a good grasp of what, the devices will sound like, what the frequency structure will look like. There's some indication that may be limited to frequencies below 1 kilohertz from the data that's been collected so far, but that's definitely a limited set. It also, from what we have so far, looks like the amplitudes aren't necessarily going to be that high, and so those are good things, I think, in this realm. But I think that uncertainty has, as Garrett mentioned, led the permitting and regulatory process to take a precautionary approach to a lot of this. So as we gather more data through TFIT and other opportunities, I think we'll be able to fill that uncertainty and potentially lower the concern there.
Yeah, that makes sense. Does anybody else want to answer what the main sources of uncertainty are for your stressor?
Yeah, I'll jump in as far as uncertainty is concerned. Anytime you incorporate animal behavior, especially animal behavior of just numerous plethora of species, you're adding uncertainty to the situation. And so when we're talking about collision risk, you could just pick fish and go to a river and an estuary on the West Coast and an estuary on the East Coast, and you're going to be dealing with a lot of different species that potentially have a lot of different behaviors, and they could be specific to how that collision risk pans out. So a big one there as well.
Yeah, I was going to say that for electromagnetic fields, it can be really challenging to see how animals use electromagnetic fields naturally. And so the combination of trying to do that for an anthropogenic cause, when we have a hard time saying why and how sharks use it without man-made cables, it's a lot of uncertainty and hard to get that baseline data.
And for habitats, there are several uncertainties. A big one is the metric. It's so diverse. It's very difficult to decide what we care about, what we need to measure, to what will make a change, what are the thresholds on everything. So there's been progress. There are working groups discussing those uncertainties. We are moving forward, but there is still a lot to explore.
Thank you all for providing your input. I think it's important to talk about uncertainty with all of these stressors. So the next question is for Molly. What are the differences between commercial off-the-shelf sensors versus state-of-the-art research technologies for measuring EMFs?
Oh, that's a good question. Okay, so we used a sort of off-the-shelf sensor that we had that was not purpose-built, designed to measure electromagnetic fields, and we sort of changed it, adjusted it a little bit so we could get that data out and tried to compare it to the top-of-the-line device for measuring electromagnetic fields. And to be honest, we have gotten almost zero usable data from the one that we tried to make ourselves. So the benefits, if it would work, would be that it would be cheap and readily available. But the problems are that's a lot of back end and front end work to try to make it get the same results, and we had to compare it to something really high quality to make sure that we were getting good data. So I'm hopeful that maybe in a second trial we'll be able to fix that a little bit, but for now can't say that the cheaper option is better.
I'll jump in with underwater noise there too. I think that is kind of a barrier. We certainly have some very advanced tools and that require a fair amount of expertise to operate and collect data that's meaningful. And that is kind of a barrier here for the developers, is lowering the cost of that instrumentation and to making it more available and user-friendly, with maybe standardized, code to do analysis that is required to report metrics. So I would say that is a barrier as well for underwater noise.
I can also speak to the commercial off-the-shelf options, or COTS as they're so often referred to. With collision risk, I'm going to go strictly to cameras in this situation, and it's almost the opposite. The high resolution, high frame rate, auto exposure cameras they seem like they're more devoted to scuba divers and getting really great high resolution pictures to show off to your next door neighbor. Whereas what we need is something that can handle really low light conditions, doesn't have to be color, and we need consistent frame rate. So in a way, the COTS that's available, we need to back off of that and go to something a little bit more simplistic to allow our automation algorithms to work properly on those. So it can go both ways.
To jump on what Garrett was saying for habitat, well, we'll take more the scuba diver options where it's better to have high quality video so we can actually identify species. But I think the highest cost would be related to going at sea with boats for deploying sampling instruments like on ROV or grab or troll. Each time there is field work involved for assessing changes in habitat, it's a lot of field time, then that's the highest cost.
Yeah, that all makes a lot of sense when you're starting to talk about the technology development and needs inside your stressor. So thank you for sharing all of the different perspectives and how technology improvements can either hinder you or make it better for your different stressor that you're looking at. So I think that's something to take note as we're looking at developing recommendations and proposing different technologies. And so just hearing those barriers that you have and differences is important. I'm excited to hear what our participants will say about some of those barriers that they're experiencing too.
Yeah, me too.
Yeah, so for the next question, Garrett, you're up. It seems like there are many ways to collect data for collision risk. Like your slides were beautiful with pictures and lots of different data collection methods. So how do we actually determine which method is best, and why would we select one over the other?
Excellent question. And early on in the process of trying to observe collision risk in these inhospitable environments, it was a bit of a free-for-all. But we're starting to pare that down a little bit. And so again, I'll use cameras as an example. If you're concerned in water that maybe is dark and or turbid, a video camera is not going to give you quality data. You're going to have to move to something like an imaging sonar or an acoustic camera, which provides really, really good resolution in these dark, turbid environments. If it is clear and there's plenty of light, video camera is definitely the way to go. It's high resolution. Another example of that would, going back to the metric like Linnea was talking about, if your metric isn't an individual animal being struck by a blade or colliding with a device, if it's just needing to know a course metric of where are most of the animals in the water column over a month or a year, you can use a simple fisheries echo sounder for that to provide information on where they are in the water column. But it's not going to give you that really high resolution detail that you're going to need for an individual having an interaction with a device. So it's going to be very scenario specific.
Thank you, Garrett. So the next question is for Linnea. Because habitat is sort of, there are a lot of diverse habitats and perspectives may differ on what habitats are most critical to study when you're monitoring the impacts of marine renewable energy to habitats. How do you address this in these different perspectives?
That's a good and tricky question, Kaylin. Thank you for asking. So I think it really depends on what the regulators who are permitting a site care about, but also the stakeholder who may be involved in the area, what they would be concerned about. It depends on what we know about the site itself, on the different species that use it, that live there, on the different habitats, on how they could get affected by the presence on the operation of a device, a MRE device. And it also depends on what the developers are willing to monitor, because if the regulator has a list long like an arm of things that they care about, a developer might be, yeah, okay, I can focus on those, but not everything. So it really depends on all these aspects, and needs to involve a discussion with all the players at the table. And so we can really use the most up-to-date and sound science that we have for this specific site on what we know about the animals and habitats, and especially if they are listed species, like endangered salmon species or sea stars that disappeared from the wasting disease, or things like that. So it's really a compilation of all what we know on a discussion between all the players.
Does anybody else have a stressor where perspectives may differ when you're looking at your specific requirements for doing environmental monitoring?
I would say along those lines, underwater noise is it's certainly how you go about collecting the data is influenced by what environment you're in, right? I guess that's a perspective in a sense. High current environment is takes a very different approach and type of measurement than going out and being in a wave induced field. So for instance, we've kind of converted the IEC documentation I mentioned has recommendations for recording around tidal environments or high current environments using drifting hydrophones. And the reason for that is because if you have a fixed sensor and you have water moving over that pressure sensor, essentially a hydrophone, the interface creates a non-acoustic pressure fluctuation, which is something called flow noise, which can contaminate your data. So if you use a drifting hydrophone, you aren't as susceptible to that. Whereas in a wave field, you can set stuff in, since you're not in such a high current environment, you can set stuff on the seafloor or suspend it off the seafloor, and you don't have that large concern for flow noise contamination. So
I could speak to perspective as well. I think collision risk has a really good sort of long-term win in it, in that when MRE first came on the scene with turbines, all of the knowledge that existed out there was traditional hydro. And these are fish are forced through these. They move really fast. There's no way around them. There's pressure fluctuations that occur. And so the first intuition that people thought of were those, a lot of fish are damaged, a lot of mortality related to those. And so we really had to change that perspective that these turbines are in open water, they're moving much slower, there's not pressure changes. So that for collision risk, that's been a big win, is showing someone an underwater video of how slow these turbines move, and you kind of have that, you see the light bulb go on, like, oh, okay, that's still a risk, but it's not nearly the risk that I had pictured in my head originally.
So you're saying if you were to see a wind turbine on a hillside and their blades move pretty slowly, you could maybe relate an MRE device to that same sort of slow movement through the water column?
Perhaps, yeah, I think that might work. Yeah, it would be, that perspective is key, definitely it is, because when you're picturing, again, the term, yeah, just the high RPMs are what everyone's imagining. So seeing that slow rotation rate would help.
That triggered something for me too. I like it, Garrett, what you said. I mean, the perspective of for noise, typically I think that approach for precaution has become from the fact that pile driving is such a loud, exercise. And that's why they're kind of is concerned. They don't know, what the effect will be here. So even drilling, can be really loud as well. And those are the two main kind of construction or industrial anthropogenic activities that we see in the coastal zone. So I think that's why that perspective that they have can be hopefully shifted as we start to make more recordings around devices, like you said, and change that perspective to, well, we're not talking about pile driving here. We're not talking about anything near the amplitude levels that pile driving shows us. So we'll hopefully be advancing things pretty quickly as we can record around more devices.
Yeah, thanks for sharing. So the next question is for everyone, and you can just round table this, whoever wants to jump in first. Are there any tools or monitoring methods that can be used to study multiple stressors?
I think I was in my collision risk section, I was discussing knowing animal use of an area to enlighten how close, or do they even approach a turbine, or do they keep their distance? And so passive acoustics would use hydrophones to listen for marine mammal vocalizations to give you an idea of location or presence absence. So potentially listening for marine mammal vocalizations and underwater noise at the same time. But Joe is the underwater noise expert, so I'm going to default that to him if that's a possibility.
No, I think that's very reasonable, and I think that there's crossover for underwater noise into Linnaeus stressor and changes in habitat as well. You may be able to monitor presence absence of animals in an area before and after an installation based on their vocalization activity. So those are both good examples.
Yeah, exactly. And there's also a crossover between collision and habitat when you use sonars on multi-beam echo sonders to detect school of fish. Those work for collision are used to monitor fish as they came close to a turbine, but we also use them to survey how the fish use the area on even without a turbine. It's a very common tool for fisheries, so that they know where their fish are. Videos are also tools that are used for, even if Garrett was saying that it's better to have low quality videos or acoustic cameras. In some areas, a video system that is used for habitat would also be used for collision. It's transferable. I think EMF might be the trickiest one.
There's change in habitat there too, right? Potentially.
Yeah, I feel like there's definitely a trend towards sort of having a monitoring package that's sort of integrated, that has every kind of sensor, so that it's measuring all those things at the same time, and maybe you can start to tease apart what's causing those behavioral changes. Garrett might know more, but I think one of the big challenges there is sort of making sure your sensors don't talk over each other and interfere with the different kinds of data you're trying to collect.
Indeed, the University of Washington had a great research project that's still ongoing with their AMP project, adaptable monitoring package, with multiple sensors, and a huge hump for their research was exactly what Molly was describing, was getting all of these sensors to be able to collect data and not create crosstalk. So if you have different acoustic sensors, you're going to have some issues there. If you're creating active acoustics, you've got a hydrophone that's listening to that as well. So certainly a challenge. And many of the multi-sensor suites are excellent because you do get those data streams, but there's trade-offs to that. Often they're centrally located, so you have really great temporal variation, but your spatial variation might be quite limited. So I know in Nova Scotia, they had a platform similar, and then I believe in Scotland, they have a bottom-mounted platform that had multi-sensors as well. So a definite solution to getting multiple data streams.
Thank you all. I think that's a great conversation to have, especially when you're talking about cost effectiveness too. So the last question I have for you is, what interests you the most about each of your stressors?
I'll start. I think that for EMF, there's just so much we don't know. I mentioned earlier that you know, scientists somewhat can't even agree if certain animals use electromagnetic fields to do their long migrations or some other magical mystical force of the universe. And I think that that's just really cool that we can help both contribute to this very specific applied, but maybe also learn a little bit about like some of the basic science of how the environment, animals in the environment use electromagnetic fields.
I'll go next. What I'm most interested with habitat is that first there is a lot of different effects that we can look at. It's not just are the fish colliding with the turbine? No, there is so much more to look at. And also the geek in me really likes that there is a lot of different instruments that we can use to assess this change. Like I was saying, it's sonars, trolls, drags, videos, scuba diver. I'm a scuba diver myself, and I'm looking forward to to use my skills to assess some of the changes in habitat. And we can use, we can also develop new technologies. There is a lot of avenues to explore still. Like I'm sure we can use AUVs to automatize some of the monitoring, like videos or water sampling, eDNA sampling, all these sorts. And so there is a lot of things we can do, and that's what I like the most. And also that the fact that not one size fits all. And so even if we're trying to get some consistency and some recommending some guidelines that would work at all the sites, might not be possible. And so it's very challenging. We might need to recommend things that work for specific cases that can be adjusted for other cases. And so that is quite an exciting part of this stressor.
Okay, I'll go. Well, I like the acoustics. I like acoustics because it's a cross, at least the application here is a really nice cross of physics, engineering, and biology. You know, the physics of the propagation, the technology of how we actually can measure sound underwater, and then biology side of, you know, how are things affected? What's the ecology? What's the effect on the ecology? I focused more probably on the engineering and the application side than the other two, but I'm learning something all the time from both of those. And I just really like sound, and reason sound is one of the reasons sound is so interesting here is because of the efficiency of the propagation of the energy, right? So as humans, we really focus most on optics as our way to navigate and communicate, right? We use our eyes. We can see farther than we can hear or most any other sense, smell or anything. So we really are optically oriented. Well, underwater, it's sound. Acoustics is really the form of energy that animals use, and humans actually use to really gain the best sense of their surrounding environment. So I like that kind of perspective and shift of applying acoustics in that kind of framework.
I guess I'm left. What was the question? I'm kidding. With a background in fish biology and behavior, obviously sort of concern for fish and MRE was what piqued my interest originally. And then having left UMaine, where I was doing mostly fish work, and coming to the lab where I was able to learn about a lot more receptors, some marine mammals and birds in this case, really just kind of elevated that. So just learning more was really what sort of keeps me going. And furthermore, I think at present, collision risk is a really significant concern for regulators. And so I see a lot of research in the future for that. So that I don't like that it's such a concern, but I am excited about a long future of the research for collision risk in marine mammals and fish and birds.
Yeah, thank you for the roundtable discussion and answering those questions. I'm sure the participants probably are going to go through those questions and think about answers themselves. And I hope that they'll share with us during our live event on the 12th. So I think we're going to talk a little bit about what happens next after this conversation. And the first thing we're going to talk about is our survey. And prior to the workshop, if you are at the workshop right now, you may have received an invitation, or maybe you just found this workshop as part of the agenda on Oceans Conference. And we'd love for you to participate in our survey. So we just launched it 2 days ago. We have around 7 responses, and we really want to hear from all of you who want to participate in this discussion. It's important to us, and we really want your voice. So please head on over to this website, and the survey is about 8 minutes long and 17 questions.
I also want to add that we want to hear from everyone. So we want to hear the voices of regulators, developers, policymakers, anyone in the industry. We want your feedback so we can best serve you with the recommendations we create. So don't be hesitant. We want all of the feedback we can possibly get, and we'll continue that conversation at the workshop. But the survey is also really helpful to get those data ahead of time. Now we'll just go around and let you all know how you can connect with us and how you can contact us if you'd like to have conversations or email us about anything.
Yeah, here's my email, alicia.amerson@pnnl.gov.
Yeah, I really look forward to hearing from other people. Not necessarily, you don't even have to be within the MRE community. If this piques your interest, or you think you have a great idea or a solution or some feedback, or just interested in this, hopefully you'll contact me. You see my email address there. Yeah, I would look forward to the conversation. Thanks.
Yeah, looking forward also to hearing anybody's thoughts. You can reach me at molly.greer@pnnl.gov.
Same for me. If you have any thoughts about changes in habitats, on what's your favorite tool to measure those changes, you can contact me at lenaig.hemery@pnnl.gov.
And I'll follow up with the underwater noise stressor. If anybody has any questions or just wants to chat about acoustic monitoring around MRE, I'd love to talk to you and invite your contact. My email there is there at joseph.haxel@pnnl.gov. Thanks.
And if you have any just general questions, or you need to talk to somebody to get in touch with somebody on our team, I'm communications lead, so I can handle anything like that. Feel free to contact me at any point. My email is kayleen.gunn@pnnl.gov. And I will turn it back over to Alicia to conclude this presentation.
Thank you, Kayleen, and thank you, Joe, Molly, Lenaig, and Garrett for such an informative video and recording today, and taking on the challenge of these new video conferences. So this was a lot of fun with you today. And participants and viewers of this video, we hope that you enjoyed our content and our conversation about environmental monitoring and technology around marine renewable energy. We had a lot of fun designing this video for the new virtual conference layout, and we hope that you'll participate in our survey if you haven't already. And we look forward to connecting with you at the live virtual workshop event, which is going to happen at the Oceans Conference on October 12th from 9 a.m. to 1 p.m. Pacific Standard Time. So we will be available at that time to answer questions and dive deeper into the stressors, the tests that we plan on performing over the next year, and we want to hear more about overarching recommendations for the document that we want to produce that will help you potentially in the field or as a regulator. So please reach out to us and find out more on our website at triton.pnnl.gov. And our program is often featured on the PNNL Instagram, Twitter, and LinkedIn accounts. And as you can see here, we just started a new Triton Stories blog. So please connect with us and check out more from our team, because there's more than who you see on this video working on really cool Triton projects. And if you want to continue to participate in the development of MRE monitoring technology environmental recommendations, please make sure to fill out the survey, leave your name and email at the end. And thank you for joining us today.